All right, before we kick off, welcome everybody. I am LIEVEN and I'm going to talk about a little extension that we got in the C++ 20 standard like 40 years late, I would say. But before, we're going to start a little quiz. Who are these? Shout out. The Jacksons, that's correct. Who are these? The Bee Gees, yes. Who are these? Oasis, yes. This. Last one. Who are these? That's always a tough one. Kylie Minogue and? Danny Minogue. Now, did anyone spot a pattern?
Yep.
They are all siblings. Brothers, sisters. So, let's start a little company, because the music industry needs our help. They have a big database, siblings in music, and they don't know how to sort it, and they need our help to sort it. Their database, they're always a little bit shy on money in the music industry, so it's a stupid factor. So, all right, we know how to do that, so let's do that. We have the database, a vector of siblings. Let's use C++ 20, range is sort, and we use a little lambda. The surname is the first key, the surname is the first key, first name is the second key, and the struct are the two members, and let's use the spaceship operator, which takes in the other thing to compare to by const reference. That's important, const reference, not by value. It's a const method. We couldn't care less about the return value, auto everywhere, and compiler equals default. You implement it for us. Ladies and gentlemen, the spaceship operator has solved the problem. That's it. That was my talk. This is C++. It's not possible, it's this easy. There has to be a catch. Okay, let's go back in time. Operators. You have the equality operators, but you also have the relational operators. So, how did it work in the past? Let's imagine we create a class magic int, which encapsulates an integer. In case we want to be able to compare it, we write the compare operator, which takes the other thing to compare to. It compares the two members, value, and its const, obviously. And we would also like to sort, or let's say let's sort. This thing is falling down all the time. So we need the less operator in order to sort. That's also very trivial to write. So yes, our magic int can be used in production. Well, if I have my magic int and I compare it to the magic number 242, this works. However, mathematics, it should also be comparable the other way around. It does not. It seems there was a design flaw in the C++ language. The integer type did not get an operator that could compare to my magic int. What a design mistake. So how do we solve that? And under the mathematics, it was already mentioned, act as an int, a good advice from Scott Myers. So what we're going to do is, let's add another method. And in this case, let's use a free method, not a member method. And the only thing this one does is, let's call the member method by swapping the operands. So the free function says, I take an integer as the left-hand side of the comparison, and the magic int as the right-hand side, and what I do is I call right-hand side equals the left-hand side, and we're calling the member method of our magic int, which can compare an integer. Now, why does that work? And why did the first one work? I didn't mention. Because the magic int has an implicit constructor. We have an advice, you should single argument constructors, make them explicit, but this is slideware. Don't do what I do, but do what I say. So use explicit constructors, but I need it to make a point. So that's why we can compare them. There is a conversion happening. The 242 gets translated into a temporary magic int thanks to the implicit constructor. And we can do the comparison. So this is not so hard yet. And A equals B, B equals A. Nice. There is another way to do that, so that we don't need two methods, but just one method again. And that's with a technique called a hidden friend. So we now have a free method again, which we consider as a friend of the magic int class. And it takes two magic ints as arguments. So not an integer, but both arguments can now be converted by the compiler. So again, we can do A equals B, B equals A. Doesn't matter where the integer value is or where the magic int value is, both operands can be converted. So back to one method instead of two. So that's a game. Unfortunately, that's not the only operator we need. We would like to have all 6 of them. Equality, not equal, less than or equal, which we can implement by either it's equal or it's less, and the other 3 by similar approaches. So it kind of looks like this. Okay, we write this once and be done with it. That's feasible. Well, we should modernize our code, so we should add no except, because those things should not throw. We would like people to not ignore our return value, because that's typically a bug, so we also add a no discard. And as Jason says, const expr everything. So we had to go back to that code over time and adjust, all right, it's a one-time thing, it's feasible. We have, of course, a lot of those structs in our code base, so it's a one-time effort multiplied by n. It's not that feasible anymore. Now, C++20 brings something new to the table, and that's the rewrite rules. If you have an equality operator on some type, and say you could do A equals B, and A and B do not have to be of the same type, the compiler is now going to help us if we write A does not equals B. The C++20 rewrite rules are going to say, okay, I will try an operator on A type, taking in an B not equal, a not equal operator. If it finds that, that's the one it selects. If that one is not present, it's going to try something else. Then it's going to say, let's see if we can find an equality operator between the types A and B, and we take the negation of that result. If we can't find that one, let's try to swap the operands and find an operator which takes a B and an A, or an equality operator on the type B which takes an A, take the result of that and negate it. So these are new things in C++20. Note, it will never try to swap the operands on the not equality operator. Don't ask me why, but that's not supported. So it's not going to try B not equals A. The same if you want to try A equals B. If that operator can be found on the type A or a free function taking an A and a B, that's the one which is going to be called. If it cannot find it, it's going to look for an equality operator either on the B type or a free function taking a B and an A. So this is already helping that we have less functions to write compared to the past. It doesn't fit all on the screen, I see. So here you see an example with those rewrite rules. So I have a magic int f1, I have a magic int f2, 2 instances, and the only thing I have implemented is the equality operator. So I did not implement the not equal operator. So the first one is f1 equals to f2. We have implemented that, so that's okay. And then we say f1 is not equal to f2. We did not implement that one, but the rewrite rules are helping us. It's saying, I'm going to rewrite this as A equals B and take the negation of that. So that works. f1 equals to 242. this will also work. F1 and 2 for 2, and that F1 is of the correct type. It can take as an argument for the comparison operator, the equality operator, a magic int. The integer is not a magic int, but we have the implicit constructor for the magic int, so it's converted to the magic int, and it works. The other way around is, of course, again, a problem. 2 for 2 is an integer. It does not have those methods. However, it's being rewritten. A equals B becomes B equals A, and it works again. And similar for the not equality. This is the result, the outcome of that. However, in order to do this, you need to activate the -stdsc++20 flag. You turn it on, you're compiling your code base, and compiler says no. Oops. And why is that? What is going wrong? If we look at this little example again, we have the magic int with the equality operator, and we also have the free function. It was pre-C++20 code, so we provided that free function in our code base, which we have seen, which says, I take an integer and a magic int, you know what, I'll swap them around. And now the code breaks. In both examples, the code is going to break, because if we take, for example, 2 for 2 equals F1, let's take that one as an example. The free function says, okay, I'm taking an int and an F1. All right, no problem. Let's swap around. Let's compare F1 with the int. We are not getting in our member function. And the reason is we can only get in that member function if the integer is converted. If the compiler sees it can do a swap, it doesn't need the conversion. The conversion is seen as something costly, as something bad. So it says, I can swap and avoid the conversion. Let's take that one. And we have an endless recursion. Swap, 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 and we never get out of it. So you had perfectly legit code. You turn on the flag -stdsc++20, because in the end we want a spaceship operator, and the code breaks. How do we solve this one? If you go to C++20 and the code base will only be compiled with C++20, you do the best refactoring there is. You throw away the method which is no longer needed. Less code, less bug, less maintenance, a pure win. If that's not possible, because the code will still be compiled with, in some projects, with an older standard flag, you cannot remove it. There are two possibilities to solve it. In the swap function, you either say, I am going to explicitly call the equality operator on my right-hand side, passing in the left-hand side. So that's the left solution. Here we're explicitly saying that's how it should be called. Compiler has no other options anymore. Or a second solution on the right is, I'm going to do this conversion myself. Because I know compiler is going to avoid conversion. I'm saying, I'll do it, compiler, you're out of the game. So those are two ways to solve the code if this happens. And you cannot go for the first option. The first option is the nicest. All right, the title was about a spaceship operator. So let's finally get to it. There are different rules at play for the spaceship operator. And we're going to see shortly what that is. The spaceship operator can be defaulted, as we saw in the little example of the siblings in music, or it can't, or it's not defaulted. There will be different rules. The spaceship operator, don't call it yourself. So don't say A spaceship operator B, don't do that. Use the regular 6 operators we know of. The spaceship operator is an implementation detail. There will be a moment where we see that we explicitly are going to call the spaceship operator, but that's at the moment we are implementing the spaceship operator. Then it makes sense that you call the spaceship operator. And depending on the support that the members of your struct or class are bringing, the defaulted one can either be const expr and no except. If your members allow that, automatically the thing that the compiler generates will be const expr and no except. So even if you don't think about it and the compiler sees, yep, this is perfectly possible, it will do it for you. And the rewriting rules we just saw a while ago will also apply to the spaceship operator. So that's also interesting to know. The spaceship operator has the highest precedence compared to all the other relational operators. And what is the return type of the spaceship operator? For now, we're going to ignore it. The only thing we know, it is something which can be compared to 0. It is of a certain type. For the moment, we don't care. Auto everywhere. But no, for now, it's something which can be compared to 0. So let's try to apply that to our magic int. So if you want to implement a spaceship operator or have it default implemented, we need to include the compare header. So for our magic int, we say, all right, spaceship operator, first argument constref to the type. It's a const method. Return type, for now we couldn't care less. We put auto and we default it, meaning compiler, you generate it for us. We see some little examples on how we could use it. So less than, bigger than, less or equal. All 6 possibilities, we get them all for free. And we only had to add 1 line. In our siblings in music, at that moment, we only needed the less than operator in order to sort a vector. But here we get all of them. And we also give an example where we sort the vector, std sort, so it's going for std less, which is going for the less than operator of your type. So this is, I think, a very good addition. 1 line, and we get all the boilerplate we had to write before. It just fit it on 1 slide in a small font. Now we can even increase the font, and it continues to fit on the slide. These are the outcomes, 0, 1, 0, 1s. Feel free to check, they are correct. So when the spaceship operator, as the magic int example we have seen, is defaulted, it gives us the 4 relational operators and the 2 equality operators. The compiler's implementation will apply the thing you want to do on a member per member basis. So the order of your struct is important. As we saw in siblings in music, the first member was a surname, and the second member was the first name. If it would have been swapped around in the struct declaration, the outcome will change. So this could have an impact if you're doing some maintenance on your struct and you decided, I like my members being in an alphabetical order. All this will still be there, but it will have a different outcome. And here's the catch. If it's not defaulted, we do not get the equality operators. If it's defaulted, we get all 6. If it's not defaulted, the equality operators are not there anymore. I said that the return type is something which can be compared to 0. That's a well-known pattern, the 3-way comparison. A operation B, this actually means, is the outcome of A operation B less than 0, equal to 0, or bigger than 0? For example, the old std string compare works in a similar way. So if we apply this to the spaceship operator A, spaceship operator B means that outcome less than 0, equal to, or bigger than 0. We still haven't mentioned what the return type is. This will come later on. The rewrites are also still in play. So if you write in your code x is smaller or less than, smaller or equal to y, if the compiler cannot find this operator, it's going to try the spaceship operator and see if the outcome of that is less than or equal to 0. If it can't find that, it's going to swap the operands. and say y spaceship operator x if this is bigger than or equal to 0. Those are the rewrite rules the compiler is going to try. So x spaceship operator equal to 0 means x and y are equal, and we will see later, or equivalent. Those are two different things. X spaceship operator y is less than 0, it means x is less than y, and if it's greater than 0, it means x is greater than y. Yes?
Question. I think I actually just taking the getting up these stocks at spaceship operator take resonance of all the publics, and it's not immediately provide third quarter there. Am I mistaken here?
If you write the spaceship operator explicitly,
Yeah.
and you use it with the other relational operators, then this precedence kicks into play. But the guideline was, try not to write the spaceship operator explicitly. So if you don't write it explicitly, you don't have to worry about that. Again, the operator not equal will not be rewritten into a call to operator to the spaceship operator. As we have seen before, it might, however, be rewritten to the equality operator, which was generated from the spaceship operator. That's a different thing. As mentioned, if the members of your struct allow it to be no except and const expr, the spaceship operator will also be const expr. So let's have a struct coordinate which has an x, y, z, and we say spaceship operator default. I leave it up to you. The doubles can be const expr. We will see with the static assert that the coordinate 102030 is smaller or equal to the coordinate 110000. The x coordinate was all enough to make the decision. Now, if the spaceship operator is not defaulted, let's take the example of the person with the first name and the last name. We implement the spaceship operator because we make it here a special one. We say we couldn't care less in our comparisons for first name, so we say we will just have a look at the last name. If we would not have the equality operator, it's on the slide, but assume it's not there, that means that the vector of the South Park characters, we can sort it. Because it's not defaulted. We have seen we get the 4 relational operators. In order to sort the vector of the South Park characters, we need the less than operator. That's one of the 4, we got it. If, however, we would also write a comparison to see if the 2 authors of South Park are identical, compiler will say no. It's going to say, I don't have an equality operator anymore. So that's why on the left bottom, we need to explicitly also add the equality operator.
Why?
I don't know the details on the why. I have wondered, and I didn't do that homework. If somebody knows why, please come afterwards and tell me, because I'm curious. Or if anyone wants to shout out the answer.
It can be more efficient for things like street.
Okay.
Not just on thighs.
Yeah. Okay, Jason says it can be more efficient as on strings. Yeah. So I'm going to assume this is correct, so thank you. Let's look at some more examples of the spaceship operator that we want to implement. Let's assume we have a struct, again, a person, it has a last name, a first name, it has an age, and it has some data. Some data we really couldn't care less about. Maybe it's some caching of something that actually doesn't matter. It needs to be not defaulted, because if we would keep the default thing from the compiler, it's going to look at the sum data member. And we are explicitly saying that one should be out of the equation. So this means if it's not defaulted, we need to add the equality operator. in case you need it. And we're going to implement it this time by calling the spaceship operator on the member. So this time we are going to call the spaceship operator ourselves. So let's have a look how this looks like. Again, some parts are not on the slide. So we have a first name, last name, and an age, and that's some data. Let's model it as a vector of integers. Let's implement the equality operator. That's very easy. First name equals to first name, last name to last name, and age to age, and we don't mention some data. Equality, check. Then the spaceship operator, which is going to give us the 4 others, the 4 relational operators. First criteria is apparently in this case, let's first check on the last name, and we think that's the surname that's most important. We call the spaceship operator. We know the result is comparable to 0. If it's not 0, it means it's less or bigger than, meaning the decision has been made and we can return. If it's 0, it means they are equal. Decision cannot be made yet. We need to investigate the second member, our second criteria, which is in this case the first name. If it's again different from 0, success of the decision. Otherwise, we need to look at the very last one. So in order to implement the spaceship operator, we call the spaceship operator. Let's take another step back. And what does compare or ordering mean? Can we always compare stuff? Can we always put an order on things? And what is equal versus equivalent? If you have hello with a capital H versus hello with a lowercase h, is this equal or equivalent? It will depend on the context. What is not a number going to do? Say I have some doubles, D1, D2, and D3, which is not a number. Let's inspect the not a number use case. Is D1 equal to D3? No. Yeah, of course. It's not a number. Great. Is it smaller than? No. Okay, I think I know the answer. It must be bigger than. No. It's none of the 3. What the hell? Come on. There must be a bug in the compiler. Let's check if not a number is equal to not a number. No, it's not. You cannot compare anything with not a number. Let's try something else. Let's put them in a vector. D1, the not a number in the middle, and D2. And let's sort this thing and print it out. We see that everything comparing to not a number gives all falses, zeros, and we seem to get a sort. The not a number moved to the end. Recently, somebody pointed me out on my recording of this talk last year in ACCU that I made a mistake, and it's correct. I thought this was working. No, it's undefined behavior, which seems to work. So, if you want to sort doubles, you need to ensure there is no not a number in the thing you're sorting. Or you need to provide your own comparison function where you explicitly deal with not a number. So that's something I learned from a comment on YouTube. In this story of the spaceship operator, there are different comparison categories. You have strong ordering, you have weak ordering, and you have partial ordering. And a stronger ordering can always be converted into a weaker one. So a strong one can be converted into weak, weak into partial, but not the other way around. That's not possible. Remember, we didn't talk about the return type yet of the spaceship operator. We said auto, we couldn't care less, and it's comparable to 0. Well, actually, the return type is an enumeration class. And it's one of those ordering enumerations. There is a strong ordering enumeration class type, a weak one, and a partial one. And that's the type that the spaceship operator is returning. The simple thing is getting more and more complex. So strong ordering means any value of a given type can be compared. And it will either be less than, equal to, or greater than. An example, integers. You can compare them, the outcome is defined. STD string. So a spaceship operator, for example, on STD string, will give something of the type strong ordering. Of course, the spaceship operator was not needed because strings could already be sorted, but if you think of a type like that, so it's either the enumeration value strong ordering less, strong ordering equal, which in this enumeration has the same value as strong ordering equivalent, or strong ordering greater. All right. Weak ordering. Any value of a given type is either less than, greater than, or equivalent. Not equal, equivalent. For example, a case-insensitive comparison of strings. Hello with an uppercase versus hello with a lowercase. Case-insensitive comparing, those two will say we are equivalent. The return type is, and the enumeration type, weak ordering. And there are three possible values: less, equivalent, and greater. Equal is no longer an enumeration value in this one. And then the weakest of them all, partial ordering. Any value of a given type could be less than, equivalent, or greater than. Could. So that means it's possible, it can be compared. Think about what we saw with not a number. It could not be compared. The return type is an enumeration class called partial ordering. It has 4 values, less, equivalent, and greater, as we also saw in weak, but there is a 4th one, unordered. So we have 3 different types for the return value of the spaceship operator, depending on what kind of ordering, the type on which you implement or you create that spaceship operator can do. Some other avoids X spaceship operator Y. I already said you typically don't write it like that, but maybe, yeah, you really insist, don't write it's equal to strong ordering equal, because tomorrow that type could change and it's no longer a strong ordering. Your code will no longer compile. Yeah, compare it to 0 in this case, or don't call the spaceship operator explicitly, and the first advice. How am I doing on time? Okay. Let's go back to our person example, and let's change the age from an integer to a double. Equality operators, still the same. Let's look at the members. STD string, strong ordering. A double, partial ordering. Now, what will the return type be of the spaceship operator? Oh, let's not care about it. Auto everywhere. No, won't work, because we have seen in the implementation have multiple paths where we return, and all of them should return the same type. It will deduce different return types. So on the string it will say strong, and on the other one it will say partial. So that doesn't work. It seems we need to take action and solve it ourselves. One solution, go for the common ground. Let's go for the weaker type. So our spaceship operator now for person says explicitly, I am returning a partial ordering. The implementation is as before. The first criterion was on the string, which was actually a strong comparison. We have seen stronger ones can always be converted to the weaker ones, so strong becomes implicitly converted to partial, works. Second one, also a string, so same thing. The last one is partial ordering and matches explicitly exactly our return type. So that's one solution. let's go for the weaker type. Or we can choose, let's go for the stronger type. We return strong ordering. That means in the third case, when we are looking at the age, we should do something. So here I am checking explicitly to the enum types, because I know what it is. I am implementing here the spaceship operator, so I have to do it. So I say, okay, less is less. Equivalent, we make it equal. Greater is greater. And what do we do when it was the other option, unordered? Well, let's say less. Let's document it, that's our decision, and be done with it. In many use cases will be okay, in some use cases it will not be okay, and then, yeah, we start to fight. The language or the library helps us out a little bit for doubles. It can convert the outcome of the double comparison to strong ordering. And it also works for not a number. So it's like, okay, I don't have to solve this myself. I will call strong order on with the two doubles as an argument. Okay. Might be okay. In some contexts, maybe in others, it's not okay. Depends. Generic codes, templates. In all our examples, we knew the types. But what if you don't know the types? T1, T2. Are they both strong, both partial, a mix? What will it be? The best we can do here is determine the common ground. Go for the weakest one, the greatest common divisor. This has been foreseen by the common comparison category template. It takes the T1, T2 parameters, and it will decide, the compiler will deduce what is the strongest comparison category I can give of this one. Maybe it's partial, maybe it's strong, maybe it's a mix of weak and strong, which means it's weak. Compiler will deduce it. A little example, I didn't write it as a template, but I'm going to use the trailing return type syntax to specify it. So I'm saying the common comparison category is the decal type of the comparison of the name, and it's not a typo. Name spaceship operator name. We're just interested in types, and nothing is going to be executed of code here. So I could have written left-hand side name and right-hand side name. No, I just said name. So this is going to be some type. Compiler will deduce it. So in this case, this will be the strong order. And then it does the same thing on value. It sees it's a double, so that was the weak one. No, the partial one. What's the strongest or the common ground on that one? And that is going to be partial. And then we just implement. So that's what you would use, that common comparison category, if you want to implement the spaceship operators in templates, where you know I need to take into account my members, of which the type I don't know yet. Let's have a look at the rewrites again. So if x is not equal to y, what is the compiler going to try? First of all, it's going to try the not equality operator on the x type. If that exists in the x type, taking a y, or the y can be converted, we're done. If that does not exist, it's going to look for a free not equality operator and says, I give you an x and a y. If it can find that one, that's the one it's going to use. Or it tries the equality operator on the x type, taking a y, and take the negation of that result. If that one is also not present, let's try something else. Let's try the equality operator on x and y, and take the negation of that. If that one is not there, let's try something more. Let's try the equality operator on y, taking an x, and then, again, negate the result. And if that is not possible, then let's see if the spaceship operator is present and what it brings to the table. So you can have the spaceship operator on your type and next to that implement one of those operators yourself. If you implement them yourself, those ones are picked and not the ones that the spaceship operator would bring to the table. Question is, why would you do that? Most probably there are use cases in the code base that we have. It's either the spaceship operator is there and we kicked out all the old stuff, or we say it's there, it works, we don't touch it. So if none of them are found, it's going to say I'm going to try the equality operator on X taking an I which was generated by the spaceship operator. And otherwise it's going to try that on swapping the operands on the Y operator. So why would it not be there on the X operator? Because it was not defaulted and we couldn't care less to add it. So it is possible that the second to last option is not there and it needs to go on the Y because it can swap. So let's try the same exercise with the less than, so with the relational operator. First thing the compiler is going to try, is that less than operator present on the X type, taking a Y? If so, that's the one we use. If not, let's try a freestanding one, taking an X and a Y. If that's not there, spaceship operator on the X type taking a Y and compare it to less than or equal to 0. Or a freestanding spaceship operator taking an X and a Y, compare it if it's less or equal to 0. And if not, try to swap it and try the spaceship operator on the Y type taking an X. And in that case, it of course should be bigger than or equal to 0. Let's add concepts to the picture. Say I want to express that I require that the spaceship operator exists. There is a concept for that, three-way comparable. So we say our template function foo requires a type which is three-way comparable. So that's very easy. So when we look at the magic int and the non-defaulted int, and our method foo, on the int it's going to work. On the magic int, and the third line will fail if the spaceship operator is not there, because it needs to be three-way comparable. And the last one will fail if neither the equality operator is there or the spaceship operator, because the non-defaulted one, you know, the equality operator is not there. So extra stuff to add to ensure that they will fit the requirement of being three-way comparable that the foo function demands on the type. Let's handwrite this concept just for fun. So what we could do is we say my spaceshipable. I can also come up with strange words. My spaceshipable requires a type T, and we say T, spaceship operator T. T, because it just needs to compile. This is not going to run, so that's enough. I don't need a T1 and a T2. TT. No. That's another way to write it. My spaceshipable 6, because I want all 6. The previous one does not guarantee me all 6. It could be 4. So I say I want all 6. So T spaceship operator T and T equals T. That's another way to reinvent the wheel myself, and the very first option is of course the best. Yeah, this is a mix of, I was just having fun with concepts. Inheritance is also important. The spaceship operator on a derived class D is first going to do its work on the base class. So if you say I have a derived class D taken from base 1, base 2, base 3, In those derivations, it goes from left to right, and in the hierarchy stack, from the lowest to the top. Now, if on a derived class you write, it's defaulted, I'm not going to write this myself, compiler, you go ahead, there is a requirement. The spaceship operator needs to exist on the base class, or it should be defaulted on the base class. So don't think if you write defaulted on the derived class, you get it for free on the base class. No. It's important to take care of. The base class has its own independent life. Because some idiot decided to derive from it, that's not the concern of the base class. So here we have the example. The base class has an integer x, it's defaulted. The derived class has an integer y, it's also defaulted. So the defaults on base and derived are met, which means we can write code like this. And the first one, it's already on the base that it goes wrong. 500 is equal, the derived is not, so the decision is taken on the y. D3 and D4, the base class is already sufficient, and the last one, everything is equal, so both base and derived class had to be consulted. And I think that's it. Are there any questions?